Yeah, thank you and welcome to Denmark. I hope you can see my front page here.
Yes.
Okay, I hope to tell you some interesting, not to put you asleep. I should try to do it swift and clear. SPIO System is a young company. We have been built on an idea to do something about optical engine manufacturing, to do similar what has happened for the electronic chip manufacturing. So you are shifting from individuals to wafer level. That's the principal idea about SPIO systems. So the company is come on, there it is. Is about almost a little bit more than 3 years ago. We have developed or invented a production platform or technology to make optical engines or devices, not single components, but optical devices. The whole idea is also to minimize and miniaturize the optical devices, so you can have more a new application just due to the small form factor of the devices, and not least to enable to scale your production and at the same time to lower the cost of the optical engines. We are out of a community in Denmark with the Ipsen Photonics Kaleido technology, so we are spin out of this ecosystem in Denmark. Today's optical manufacturing of optical instrument is quite old. It's mostly built off of discrete optical elements that you put together into a box, and that assembly can easily account for the majority of the cost for each optical instruments. And also, it's very hard to scale on short term from a few items to hundreds or even thousands and millions. And also, larger component or larger instruments is also more sensitive to external environments, make it less robust. That's all things that we would try to overcome with our technology. We want to transfer it to wafer level production, meaning that we are making components on wafer level, means that you're doing thousands of optical components in one operation. So each component is less costly. Also, we have the greatest advantage to do assembly on wafer level. So you avoid putting the things together when you have dies into individuals. And known from the chip manufacturing, it can easily increase your production capabilities. If you do that, you have less need for equipment, also less manpower. And that's really a nice time we see this geopolitics that you want to produce locally here. So we intend to be able to do it locally here, maybe not Europe or in Denmark, but also locally in Europe. And a smaller form factor also means less, more robust to external environment impact. So we are driven up from the basic idea to do everything on wafers, make optical engines out of wafers. So we don't have that much ambition to revolutionize the optical, let's say, functionality, but we can do the same product, same engines on a smaller form factor. Yeah. What are we going to do? So this is a generic process, not intended for automotive lighting, but it could be part of the optical supply chain for maybe not the headlight, but also for interior lighting or sensing. We are working, as Oliver from Delo mentioned, we're working on resins that we're imprinting on wafers, glass wafers. So we put a liquid polymer on a glass wafer, and we imprint these micro optical features in this polymer. It's not as most we are seeing plate-to-plate imprinting, but roll-to-plate, mean that we have a very high capacity from this technology alone, just because it's an inline process. It's coming from the holographic industry, or on the back days also from the newspaper. So the same addressing to make volumes production. To make this replication, you need a master for that. We are sourcing partly in-house here, but also from other vendors locally here, or suppliers, also universities around Copenhagen. It's not a one kind of optics on the wafers or so the master. It's a hybrid master, so you have more functionality on the same master. When implemented these wafers with different kind of optics elements on it, you are put more wafers together, meaning that you're stacking wafers around it, bonded with bonding glue, and also you can make multiple layers of different optical elements put together. So when you combine the stack, you made an optical engine on wafer level. And finally, you need to dice it to have the optical device ready for further integration. So by this method, you can do, ideally you can do hundreds or thousands of these optical devices on each wafer stack. So we can cut out a lot of assembly costs for the individuals. So you do a lot of you do the assembly on wafer level, meaning that even that you're using longer time for making the stack, that the time spent on each module is really a fraction of what it is today. And also by this method here, by bringing in more wafers together, we can have a very high degree of optical signal processing on a very small cubic footprint, because we have not only one layer, we have multiple layers. So we have and you can bounce the light up and down through the stack here. So we can have a really high and compact optical processing. So what do we have in our toolbox? We have all the conventional optical elements we can combine together in our optical design. You have the lenses, standard spheric lenses, but also torics and parabolic lenses. We have all the micro prisms, micro mirrors can put in, and also we can add gratings, ordinary triangular gratings, binary gratings, slanted gratings is a little bit hard to replicate, and freeforms mean that you can in shape. All these boxes, all the tools you can combine in a single master. Of course, it's very hard to replicate gratings with lenses, but we have seen some good progress on combining different kind of optics in one wafer. I think we have seen before how UV nanoimprint lithography is done, so we wouldn't tell that much about it. This is more interesting from end user perspective. This is an example of a double layer of wafers that combined a small module for a telecom receiver application. So we see here the green is the glass wafers, and the yellow is the resin that's becoming polymerized with all the optical elements. So this module here is 2.5 by 2 millimeter, and you have 6 lenses, 2 mirrors, some filterings, polarization filters in between. So a good example of a user case for our technology. So the summary here, we can opportunity with SPIO is we can miniaturize the optical engines or devices. We can also, that was not intended, but new application seems to be a door opener or small form factor optics to be a door opener for new applications. A good example is if you want to monitor the glucose content in blood. If you do that on wearable optics, you need a really large case to wear. But with our technology, we can have a smart watch size of measurement on the body. We can scale the volume. Also, we can have a true hybrid optical functionality, meaning that we can do more than just lenses or mirrors in one wafers. The challenge, of course, is that it's very unmature technology still. And also we need to figure out what is the manufacturing tolerance in the high volumes. Still, we use active alignment of the wafer, but one of the challenges would be that we would like to have passive alignment of the wafers in the assembly process. And then the typical question, what can you do for us? We would like to in-source meter structure or DOEs in our toolbox. We know from our lithography that we can imprint it, but we need a source of master for it. Also, the coatings, we do coat the polymer for making as a mirror, but also coats with AR to avoid backscattering. So we would like to reach out to companies that can do these kind of coatings on polymer surface without any surface degradation. And finally, we would like to take the next step to do, let's say, an integration step also to the actual components. It could be to do wafer level assembly on detector rays, meaning it could be silicon wafers with a silicon detector rays that match our pitch on the wafers, or opposite, we match the standard wafer. So I hope you didn't fall asleep, but that was my presentation for today. So it is a quite new approach to production. So please reach out if you're interested. We can at least have a chat for what we can offer to you.